All right, let's take a look at the ideal gas law. So the ideal gas law is our PV equals nRT. So instead of a condition 1 equals condition 2, like we've looked at before, now we're just looking at a straight set of variables. So with all of those different individual experiments that were done, comparing pressure and volume, or pressure and temperature, or volume and temperature, etc., how did we get from all of those individual relationships to here? Well, one of the ways we got there is through what is called kinetic molecular theory. So kinetic molecular theory lets us look at all of these different relationships and understand how gas particles behave. So 5 key points of kinetic molecular theory: that our gases, we've got these particles, they move in straight lines at any given instant. So if I'm a gas particle, I'm zooming along in a straight line. I'm not going in a circle, I'm not going in a curve, I'm going in a straight line. Okay? Gas particles, super widely spaced. All right? There's more empty space than there are particles. Gases are going to go in rapid motion. Okay? We're going to go boom. If we collide against something, boom. We collide against something, boom. We collide against something. In an ideal case, we're saying that there's no loss of energy. Okay? Ideal case, no net loss of energy. Because they're so far apart, these intermolecular forces that would attract or repulse them are negligible. They're going to behave independently. So this is why gases are able to be miscible and mix with each other so well. And then that average kinetic energy is proportional to the temperature. Higher temperature, more moving around. Lower temperature, less moving around. Okay? Which led us to be able to interrelate all of these together. Okay, looking at Boyle's law and Charles's law and Avogadro's law with everything that was fixed till we get to our ideal gas law. Now the variable we haven't looked at yet is R. R is a constant, and there are 2 different versions of R. So when we started off looking at gases, I mentioned that when we deal with gas problems, pressure needs to be in atmospheres or torr, or millimeters of mercury, since torr and millimeters of mercury are exactly the same thing. And so we get this: pressure, atmospheres or millimeters of mercury, or torr. Volumes in liters, N is moles, T is temperature. And then we have 2 different gas constants. We have one gas constant if our pressure is in atmospheres, and we have the other gas constant if we're in terms of torr or millimeters of mercury. And so when you're solving these problems, you need to look at what unit your pressure's in and use the appropriate gas constant. So let's try one. All right, so we have sulfur hexafluoride. Let's see what we've got here. Okay, it tells us that we want to know the pressure, so calculate the pressure. So pressure is going to be a question mark. Okay, we've got moles, 1.82. It says we have a volume of 5.43 liters and a temperature of 69.5 degrees Celsius. Okay, it doesn't give us a pressure, so we can use either R. I default to using the 0.08206 liter atmosphere one because that's the one that I've used most frequently. Okay, because if I solve PV equals nRT for R, remember we get that PV over NT, so liter in atmospheres, pressure and volume, moles Kelvin, moles in temperature. Okay. In this case, we want the pressure, so we're going to solve for P. So P is going to equal nRT over V. Okay. All right, so let's plug it all in. So we're going to get our 1.82 moles. All right, then we're going to get our 0.08206 liter atmosphere, mole Kelvin, and then our temperature. What do we need to do with our temperature? So what units is this in for R? It's in Kelvin, remember. Temperature needs to be in Kelvin, so we convert this to Kelvin and we get 342.65 Kelvin. So 342.65 Kelvin all over our 5.43 liters. And we do that, we're going to get 9.42. Okay, so our liters cancel, our Kelvin cancels, our moles cancel. We wanted pressure, and we're left with pressure in terms of atmospheres. Okay, so there's our pressure. All right, so here's another one. This one I want you to try. Okay, so we've got an air bag with a volume, a pressure, and a temperature. We want to know how many grams of nitrogen are in the bag. So if we have PV equals N RT, okay, if we have a pressure, a volume, and a temperature, and we have an R, what variable can we solve for? Well, if you said we can solve for moles, you're correct. And so if we know moles, can you do moles to grams? Yeah, with the molar mass. So nitrogen is 28.02 grams per mole. Okay? So this one, we've got millimeters of mercury. So this is where you will want to use the 62.37 liter torr mole Kelvin R. So remember, millimeters of mercury and torr, same unit. Okay, so try this. All right, I want you to try this one on your own. Define your variables. Okay, put everything in the correct units. So there's at least one thing you're going to need to convert. And then try to solve first for the moles and then do your moles to grams conversion. All right, let's see how you did. So when you got moles, okay, you should get PV over RT, and you should have gotten 1.60 moles. And then from that, you should have gotten 44.8 grams. Okay, we had a volume of 35 liters, so 2 sig figs. So when all is said and done, this should round to 45 grams of nitrogen in the air bag. Now, a lot of this gas law stuff is done at room temperature, right? But sometimes we work at what's called standard temperature and pressure. So standard temperature and pressure is 0 degrees Celsius or 273 Kelvin, or the slightly better number is a 273.15 Kelvin. Okay, and then you have 1 atmosphere or 760 torr. Okay, so let's see if we can get the volume of 1 mole of gas at STP. So our volume is nRT over P. So STP, we've got 1 mole. Okay, if we're leaving in atmospheres, we'll use our 0.08206 liter atmosphere mole Kelvin. Okay, now STP, the standard temperature, is 0 degrees Celsius or 273.15 Kelvin. Okay, and standard pressure is 1 atmosphere. And this is really nice because anything divided by 1. And what you're going to get is this number right here, 22.414 liters. This number has a special name. This is what we call the molar volume. So at STP, 1 mole of an ideal gas has a volume of 22.414 liters. Okay? So what we say is we have 22.414 liters per mole. Okay? So this has some interesting implications. So let's take a look at this next one. What volume will 3.21 moles of neon occupy at STP? Now, we could solve PV equals nRT. That's totally valid. But remember our molar volume, because we're at STP. We have our at STP, we have our 22.414 liters per mole. So what if I did this? What if I did 3.21 moles times 22.414 liters per mole? So when you're at STP, you don't have to solve the PV equals nRT if you're just going between moles and liters. You can do it this way, and you'd get 72.0 liters. So it works out really nicely there. Okay? All right, and so that is using our PV equals nRT.